This is called the iliac crest. It's the top of the pelvis. So we use that as a marker at the iliac crest, and we take a tape measure around. We actually put, to do this correctly, you have to put, there's actually skin markers that you can put a mark here and a mark here, and then go all the way around and get a good measurement around the waist. Now this gets harder if you have any class 1, class 2, or class 3 obesity to capture. So the measurements start to become more difficult, and also we call this user observability. So if you collected it on one person and you collected it on the same person, you may not come up with the same measurements because you are two different people that are doing the measurements. And so there's some variability in the people who are doing the measurements. CDC is actually really terrific at getting these measurements down. Now the World Health Organization does this differently, and this is why we have European data here, because Europe and the rest of the world tends to go by what the World Health Organization suggests. And what they do is they go from the iliac crest to the bottom rib, the lowestmost rib, and they mark the midpoint between the two. And they take the tape measure around that midpoint. It's a little bit more difficult to do. So the way the US researchers have told me is that you need to have one bone as a measurement, as a reference point, and do it around that bone. So they're using 2 bones as a measurement. So if you think about that in terms of just getting a good measurement, can you see the issues with having 2 bones? You know, now you have to have Contricia and Corinne would have, for example, to agree that this was the lowest bone after feeling around, and then agree that this was the topmost bone, and then mark the midpoint perfectly, and then get the circle around. And now imagine 50 patients coming in a span of 2 hours. Right? It's going to be very difficult to do that quickly. So that's why in the NHANES we actually have 1 bone. One interesting thing that the United States does, and several other countries do this too, we sweep out through the nation, the CDC does, every year through mobile exam carts and collects data on all the people in the US, as many as they can get. About 10,000 per year is what they get. And they do all of these measurements, and about 10, and they're perfect at doing it. And they're getting better and better at doing these things. And they even have like a DEXA machine, which I'm going to show you in a second what that is. So they get X-ray measurements on people, and they have everything in there. Every race is represented. They have midgets in the pile. They have everything that you can imagine. So it's a representative sample of the United States, so they can assess the health of the United States. Korea does it. England does it. Not every country does it. India, you're going to have problems. India, you have problems organizing anything. Organizing something of this magnitude is really difficult. And I believe China has started doing it. So they have a nice top-down management system that allows them to do this. So what I'm showing you here is 2 sets of measurements. The left measurement that says Beckencom, that's the World Health Organization measurement of a waist circumference. And the right is a waist circumference by the NHANES, or the CDC protocol. And what I'd like to do is I'd like to compare the 2 against each other and see if there's agreement between the 2. So one of the things I could do is just plot one against the other. So I'm just going to highlight. So the first step to plot. So now I'm going to upload this on YouTube right away so that when you're doing your own stuff, you can see, you can just look at the YouTube file. And you go to Insert, go to Scatter, click the Scatter plot. And I like to make these look a little bit nicer, so let me click this. The x-axis is always going to be what your first column is, just like when you're plotting points. So that's waist by WHO, World Health Organization, and this is waist by CDC. And then what I can do is just fit a line through it. So I select the data, right-click, and then add trend line. And I click these display equation and display the R-squared on the chart. So let me blow this up so you can look at it. So recalling from the last time we did this, the R-squared tells you how good of a relationship there is between those 2 sets of data. So what do you think with this R-squared? The closer that number is to 1, the better of a correlation you have, or a relationship you have. This is 0.5. So 50% of the variance of one measurement can be explained by the other. It's not terrific, it's okay.
Then you have two other numbers. You have this number over here, the 0.6597, and the 33.977. This number here, 0.6597, is called the slope. And the other number is called what? It's called the y-intercept. So these are the familiar slope and y-intercept you learned in math class, correct?
Y equals mx plus b?
That is, right, this is what it is. So they tell you something. And I think we in math, as math teachers, believe we tell you what it means. But somehow, looking at bio majors now, I don't think we're doing it right. So I'm trying to do this differently. So the slope is 0.6597. So you could say, if I wanted these two, if I wanted to argue that these two numbers were in agreement, these two sets of data were in agreement, then that slope should be 1, and the y-intercept should be 0. This should be the line of identity. The y's and the x's should be all the same. The distance that slope is away from being 1 tells you how off it is. And it tells you if it's underestimating or overestimating. We can't see that perfectly now, but does this line lie below y equals x or above y equals x? Is the slope higher or lower than 1? It's lower than 1. So what that tells you is that these numbers are lying under these numbers. That makes sense, right? If you measure here, that's going to be a smaller, at least on me, it's smaller here than it is around here. So that makes sense, right? The y-intercept should be 0. Otherwise, right, y equals x is a line of identity. Y is equal to x. We don't get y equals x. We get something off of that. So we get a shift. It's like up by 33. So it's somewhere else. And so this tells you that they're not in agreement. So it's not as clear to see that it's not in agreement. We're going to do one more thing, okay? Oh, let me ask you one question. As the waist gets higher for who, does the waist get higher for CDC? Okay. We say the line is trending up, right? So when the waist gets, so that's good, right? The bigger waisted people measured by who, or also the bigger waisted people measured by CDC. That's a good thing. If it was going the other way, bad, very bad. So this tells you, that because the slope is positive, that relationship is holding. So this is how you want to evaluate. Most of the time when you look at data, you look at that trend. And in fact, I showed you that with the bite rates, right? We look at the trend of, do people who are bigger eat faster or not faster? I want to look at that trend. So that's what I'm looking at. So I'm going to show you one more thing, and then I'm going to show you some other data which I have to shut off the video for. Okay, so one of the things that we do when we look for agreement is we plot what's called the average against the error. What do you think is the better measure, by the way? I think I was opinionated here, but what do you think is the better measure? Iliac crest? To get better measurements across the board. Or the midpoint? USA. All right, so I'm going to say that the USA column B is the gold standard, and I'm going to see how well who does against the gold standard, which is us. So I'm going to calculate the average first. The average is take A2 and B2 and add them and divide by 2. So you put an equal sign first. A2, you see that the cell lighted A2 lighted up, plus B2, and then I'm going to divide that by 2. So the average goes into this section over here. Error would be the error. Actual minus the second measure. So the actual would be B2, because that's my reference, and I'm going to subtract off A2. And that's going to tell you how off they are. And this is in centimeters. So it's 12.5 centimeters off. Now if I won't type that for each one, I'll just highlight both of these cells, go to the bottom right corner, and you can see that little cross, and bring it down. And I get all these. You see this, all these negatives? Underestimation. That's what you're seeing. So I'm going to go down here and do one last thing. I'm going to calculate the average of the error. called bias.
So it tells me that on average, the World Health Organization measurement of waist circumference is lower than the difference is underestimating, right? Because actually it's negative, it's overestimating, it's too big. So we're getting a too large of a thing. The actual minus the World Health Organization was negative on average. If I graph these two against each other, what should the error be if it was a perfect, good agreement? 0, right? So is that average 0? No. So we say it's biased. If I plot one against the other, average against the error, I can see more things, and it's all lines. One more time. This is not going to be a pretty blonde Altman, but I'm going to show you what this looks like. Let me do this. I'm going to put a trend line in this too. Okay, here we see something interesting. Maybe you don't see it, but I see it. Okay, first of all, if it was a good agreement, all this data should be hovering around the line y equals 0. But it's not. It's hovering around the line y equals -4, the average. That's where it's hovering around. The second is my error gets worse and worse the bigger the waist becomes. Does that make sense to you? Right? That would make sense, right? Because I just told you, even in our clinic, sometimes the students struggle with getting a good measurement of waist circumference. So that makes sense. And in fact, it tells me that the CDC minus the WHO gets more and more negative the bigger the waist is. So that's telling me that the WHO measurement is getting too large in comparison to CDC, because it's negative, right? So that means this is really big compared to this. So that's telling you that there's a trend for the WHO to overestimate the amount of waist circumference there is as the person gets bigger and bigger and bigger. That's what it's telling me. So here I am, all I'm doing is evaluating this line. I can see it from the slope. See the negative slope up there? The slope is negative. So that's telling you that it's worsening in the negative direction. The error is worsening as the waist gets bigger and bigger. This is average waist size. So, and the y-intercept should be 0. So it's not. So it tells you that it's got bias in it, that it's not a good agreement. So my analysis of this would tell me that the WHO and the CDC do have problems. There are articles that say that you can switch one and the other and it doesn't matter. It does matter. That's what this is saying. Okay, so how will I test you on something like this? I can give you finished things like this and ask you questions like, is it getting better or worse as the waist increases? Is there good agreement or not, and why? So these are the kind of questions I'm going to give you, like give you an actual picture to look at. Tell me what the slope is. Tell me what the y-intercept is. Tell me what the slope should be. So I could give you either one of these pictures or the other. I could give you this one over here. And ask you, what should that slope be if there was good agreement? Should be 1. What should that y-intercept be? How far off is it? Is it off, which direction off is in it? So I can ask you those kind of questions. Maybe I'll give you samples over the next week so you can practice looking at things like this.
How would you be able to tell what the slope is?
You get it from I can tell you just by looking at the line that the slope is positive, but see that thing where I click write the equation and write the r squared? Mm-hmm. That's the equation of that line. So see that 0.6597? That's the slope. It should be 1. It's not 1, it's smaller than 1.
Why should it be 1?
If there's good agreement, right? If someone wants to argue, which they have papers on it, you can look them up in PubMed, they argue that it doesn't matter if you measure it here or measure it here. The results are the same, right? Well, if that's true, then that slope should be 1, because it means that the waist circumference evaluated here should be very close to the one evaluated here, and it's not.
It's not biased at all, it's because they're not matching.
They're not matching. Right.
I need both of these pictures, by the way. I need that one, which tells me the correlation between the two, and I need the other one that tells me about the error to get the agreement picture. There were 2 statisticians named Blonde and Altman that got into medicine, I think in the 1980s, and they criticized biologists and medical experts because they only graphed this one. And they said to know true agreement, you need to look at both. You need to look at the error and see if it actually is flattening to 0 and calculate what we call the bias. The bias tells us it's not 0, it's 4 centimeters off from being 0.